Hi, everyone. Thanks for having me. My name is Evan Hall. I'm a postdoc at MIT. Previously, I was a graduate student at Caltech working on LIGO. So I'm going to talk to you today about, if I can share my screen. Yes, the past, present, and future of gravitational wave interferometry. Although I think I promised Sarah that I would not spend too much time in the past. So just to set out the very basic principle here, when we're talking about gravitational waves, we're talking about a metric perturbation that effectively is a strain in space-time. So we usually use the letter h to denote the strain. So it's a fractional change in the length of an object. So when a gravitational wave passes through an object, it causes this this strain that in one direction it compresses, and then in the other direction it stretches. And we usually, so a wave, we say it's oscillatory. And so what I'm showing you here is just how the stretching and the squeezing progresses over a period of the wave. So in terms of sources, there are many different things that can cause gravitational waves. Sort of the first source that you learn about when you first learn about gravitational waves is a binary star system, or a binary system of stellar remnants, I should say. We usually think about neutron stars and black holes orbiting each other. So when you have an orbit like this, you remember from classical sort of Keplerian dynamics that the orbit is just a fixed sort of ellipse. In general relativity, you find out that there actually is this term that causes energy decay in the form of gravitational waves. So the orbit decays and it gets tighter as energy is lost to gravitational waves. And there is a formula that describes how that happens. This is quadrupole formula, so it relates the gravitational wave strain on the left-hand side, this h, to how the quadrupole moment of the system changes. This is Qij. And then the strength of the wave, because it's an amplitude, it decays like 1 over the distance from the system to the observation. So in this case, for a simple binary system, roughly the quadrupole moment, it goes like the mass times the square of the radius, because we need the double dot here. There's 2 factors of the frequency, so it's we get twice the orbital frequency squared. That's roughly how this scales. And so if you take these formulas and you put some numbers to them, so you take a system that's 10 solar masses, and maybe it's a few times the Schwarzschild radius of that mass, so it could be 100 kilometers. That works out to an orbital frequency of a few hundred hertz. And then based on what we've seen with LIGO, we can say that maybe a typical distance is something like 400 megaparsecs. When you put those numbers together, you end up with a strain that is about something like 10 to the minus 21. So a part in 10 to the minus 21. That's obviously quite small. And so it's quite challenging to detect. So it clearly requires a precision instrument. So there are many different ways to detect gravitational waves. I've shown some of them here. These are maybe the ones that people mainly talk about. So at the very, very low end in frequency, there's cosmic microwave background measurements that have been going on for a while now. There's pulsar timing. You use the pulsars as clocks, and then you look for perturbations in their pulses. Going up in frequency a bit, there's time delay interferometry. That's what space-based detectors like LISA are going to use. What I'm going to talk about today actually is Michelson Interferometry, specifically Michelson Interferometry on the ground. And then there's also, so the resonant bars have historically been important. And then there are also other proposals like atom interferometry, torsion bars. But like I said, I'm going to focus particularly on what I've shown here, which is the Virgo detector in Italy. I mean, I'll talk about all of them, but the picture here is Virgo. So how do these things work roughly? So most of you probably remember from learning about relativity that there is experiments involving Michelson interferometers. to demonstrate special relativity. And how does a Michelson interferometer work? Very roughly, you have two test masses and a beam splitter. You take a laser, you shine the laser on the beam splitter, it splits the light. Light goes down the two arms, reflects off the test masses, comes back and recombines. If the arm lengths are balanced, then the light interferes destructively at the beam splitter, and so it all goes back towards the laser. None of it goes out towards the detector. But if the lengths become unbalanced, then the interference condition is changed, and so some light shows up on the photodiode. Now this turns out to be a very good system to measure gravitational waves because as I mentioned before, the strain that they produce is differential. So they make exactly the signal that you want to see. They make one arm shorter and one arm longer. On the other hand, one of the things that you have to worry about with this instrument is laser frequency noise. But because the instrument is differential, most of the laser frequency noise gets canceled. So you've made an instrument that is sensitive to gravitational waves, which you want to measure, and it's insensitive to laser frequency noise, which you don't want to measure. So that's roughly how this whole business works. Just to give some idea of the scale. So the signal strength, as I said, is very small. It's proportional to the strain times the length, because ultimately you're reading out a distance measurement. So it's in your interest to make this instrument as long as possible. So that's why you end up with these kilometer scale instruments. At the same time, the noise that you measure, particularly the shot noise, it depends inversely on the laser power. So it's also in your interest to make the system as optically powerful as you can. So the instruments that we use are quite, they use a lot of circulating power. And in fact, we actually use not just a simple Michelson, but we actually use multiple extra mirrors to increase the amount of power that circulates in the instrument. So these three mirrors that I'm showing, we have two extra test masses. We additionally have a third mirror that's called a power recycling mirror, and the whole business there is to just increase the amount of stored power. There's then this additional mirror that I've shown between the photodiode and the beam splitter. That mirror tunes the bandwidth. It's called the signal recycling mirror. But that's sort of roughly, this is how modern laser interferometers are laid out to measure gravitational waves. It's this sort of compound optical system. At the end of the day, is basically a Michelson interferometer. So in terms of how they receive the signal, if you look at the antenna pattern of these instruments, they're pretty much omnidirectional. So these are you can see that roughly you can't really tell very well with a single instrument where the signal comes from on the sky. And they're also they're sensitive to both polarizations at the same time. So you can't distinguish the two gravitational wave polarizations. So it's in our interest to operate multiple detectors and to operate them jointly as a network. That's how you get the most information out of the signals that we detect. So it's just, it's essentially aperture synthesis, like with the network of dishes. So the network as it stands today looks like this. There are two LIGO instruments in the United States. They're 4 kilometers. There's a 600-meter instrument in Germany. There's a 3-kilometer instrument in Italy. It's called Virgo. We are constructing a third LIGO detector in India, also 4 kilometers. And then there is a 3-kilometer facility in Japan called Kagra. It's a bit of an outlier. It's underground. It uses slightly different technology. But again, fundamentally, these are all the same, sort of Michelson topology. So if you actually look inside these things, if you look at what the test masses really look like, this is a picture of an advanced LIGO test mass. You can see that there's a person for scale. These test masses are typically tens of kilograms for reasons which I'll talk about later. They have to be heavy. And they have to be made out of high quality material. So most detectors use fused silica, so just very high quality, very pure glass. The Kagra detector in Japan uses sapphire, and there are talks about using other new materials for various reasons, which I'll get into later. And so to turn the test mass into a mirror, it's not just enough to have the glass. You have to apply a coating to the front of it. And so we use dielectric thin film coatings that are made from metal oxides. That turns it into a very, very high quality mirror, very low loss. The optical loss in each of these things is something less than probably 50 parts per million. So they're very, very reflective, very, very, and they're very polished to keep the light, to keep the phase fronts from distorting. So the test masses are suspended because the ground is relatively noisy. The motion we think the motion is small. It's something like a nanometer per hertz, around 10 hertz. But even that is just far too much. It totally obscures any sort of gravitational wave signal. So these are suspended from multi-stage suspensions. They're typically maybe 1 meter to several meters high to get the desired mechanical filtering. So what I've shown you here is an example of the Kagra suspension system. You see it's many, many stages, with the goal that the test masses have to move at a level that is commensurate with the kind of fluctuation that I'm trying to measure from gravitational waves. So it needs to be better than 10 to the minus 20 meters per hertz. So we're looking for more than 10 orders of magnitude of mechanical filtration to remove ground motion. So these suspensions are very, very complicated and they're very high performance, but it's something that we absolutely need. So if you look in a bit more detail about what the noise looks like in these things, so I hinted that there's a shot noise, but that's not the only noise that we have to worry about. So this is showing you this is a noise budget for LIGO, what we call LIGO A+, which is where we think LIGO ought to be in 2025. It's showing you on the horizontal axis, it's Fourier frequency, so it's the frequency of the gravitational wave that you measure, and then the vertical axis is the noise in the system. Obviously, less noise is better, so lower on the plot is better. This is specifically for LIGO, but if you look at the noise budgets for Virgo or for Kagra, some of the traces move around, but it's fundamentally the same set of things that people have to worry about, and they show up on the plot in sort of more or less the same place. So I just wanted to go through a little bit about sort of how these noises arise and what we do about them. So, if you look at any of these detectors, sort of the most obvious feature that you see is the vacuum system, right? So we have to build this L-shaped tube that's usually something like a meter wide and many kilometers long. This in particular is showing you LIGO, the Livingston detector in Louisiana. So you see there's this tube of steel, and it's special stainless steel that's been specially treated and specially baked out with electric current to remove problematic gases. So we have to evacuate this to what we call ultra high vacuum, so down to less than a micropascal, and really have to pay attention to particular species like water, for example, that on their own would take forever to desorb from the surface. So anyway, there's a whole science behind the vacuum system, even though people sometimes take it for granted. And the end result, as I've shown in the plot, is that we are able to get the optical path length fluctuation from residual gas down to the level where it needs to be, where it's not significantly impacting the overall noise of the detector. So quantum noise, as I discussed before, of course, there's only a finite number of photons in the detector at a given time. That means that there's a photon counting noise, which is shot noise. So naturally, that drives us to very high power to reduce the photon counting noise. But that's not the only quantum noise, because the photons have momentum. There's also a radiation pressure noise. So the stochastic momentum impinging on the test mass moves it around. It creates a noise, and so that's where the test masses have to be heavy. That's why they're tens of kilograms. And so these two sources, when you put them on the noise plot together, they make up the quantum vacuum noise that I showed earlier. So high laser power and heavy task masses, they're not the only two ways that you can reduce the quantum noise. There's a third way that's a bit more exotic, and that's called squeezed light. So I talked about the photon picture, but actually in this case, it's a bit more natural to think in terms of quantum mechanical uncertainties on the field in the continuous sense. But the point is that the electric field in the interferometer has 0-point fluctuations, or vacuum fluctuations. And for generating quantum noise, what is important is that these fluctuations enter from the dark port of the interferometer, from the output port. So what we do is we actually, instead of allowing the basic unsqueezed vacuum to go into the interferometer, we actually prepare a specially squeezed vacuum state. So we use a nonlinear crystal to basically to engineer correlations between the two quadratures of the field, and we send that into the interferometer instead. And the result is that indeed we get a noticeable reduction in the quantum noise of the interferometer, and this was used during the third observing run to reduce the shot noise. So if you look in detail, you actually notice the noise gets a bit worse at low frequencies. That's because, consistent with the Heisenberg uncertainty principle, if you make the shot noise better, you end up making the radiation pressure noise worse, or vice versa. There is a way around that called frequency-dependent squeezing, but that's a detail. That's being implemented for O4. So thermal noise. This is another whole set of noises that we have to worry about. So all of the materials that we use, the suspension fibers, the test mass substrates, the mirror coatings, they all have thermodynamically driven fluctuations, and so they all lead to random motion of the mirror surface, which makes a noise that obscures any sort of gravitational wave signal that we might want to detect. There's a result in thermodynamics called the fluctuation dissipation theorem, and the upshot of that is that basically, if you want to reduce the amount of fluctuation in your system, you have to reduce the amount of dissipation. So we have to find materials that have very, very low mechanical dissipation, so sort of microscopic molecular dislocations and stuff like that. And so that really cuts down on the number of materials that are available to us. So it's sometimes a challenge to find a material that is suitable for our use. And in particular, right now, LIGO and Virgo and Kagra and the gravitational wave community as a whole are really trying to find a better mirror coating. Because if you look at the noise budget, what you find is that really in the most sensitive part of the instrument, we're limited by thermodynamic fluctuations of the mirror coating. So that's something that occupies a lot of R&D time, is to find better coatings. So the other major category of noise is the geophysical noise. So as I said before, the ground is always moving. There's just ambient seismic motion. And I mentioned that we have suspensions, and the point of the suspension is that, the ground shakes the top of the suspension, but because of mechanical filtering, it can reduce the amount of vibrational motion that makes it to the test mass. There is a second effect, which Michael has worked quite a lot on, which is this direct gravitational coupling of the ground into the motion of the test mass. So this is not a vibrational coupling. This is just the direct force of gravity that comes from the fact that the ground is moving and it pulls on the test mass. And this, obviously, you can't screen gravity, so you have to come up with some other way to get rid of this noise or reduce this noise or sense this noise. And so what people are working on now is what's called Newtonian noise subtraction, where you use an array of seismometers to predict, based on the measured ground motion, how much the test mass is moving, and from that you can subtract off the noise. You can't do it perfectly. You can't do it to an infinite degree, but you can do it. Hopefully, we hope to do eventually a factor of 10 subtraction of this noise. So that's the geophysics, and so you notice that the slopes on these are quite steep, and so the upshot here is that really the geophysics is the reason why you can't do very, very low gravitational wave interferometry on the ground. So if you want to go down to below a hertz, if you want to go down to millihertz, you really have to go into space, and so that's the realm of LISA. That's why LISA so at least is in space, if you want to look at millihertz gravitational waves. So coming back to the overall noise budget. So this is, as you can tell, these are theoretical curves, right? These are the noises that depend on more or less fundamental physics, quantum mechanics, thermodynamics, stuff like that. The truth is more complicated. So this is a real noise budget that was generated for the third observing run for Hanford. And as you can tell, there are more noises than what I showed on the other plot. So I'm not going to go through them in detail, but this is all just to say that there's a reason that when we turn the detector on, it doesn't just work at design sensitivity. There are many, many more noises that have to be understood and characterized and then gotten rid of. That's why it's always a sort of a years-long project to reach the goal sensitivity. So in terms of goal sensitivities, this is a plot. This is a timeline of where LIGO and Virgo and Kagra intend to end up in 2025. So we were, of course, here in 2021, preparing for the fourth observing run, which will have sensitivity improvement over the previous observing run. By the fifth observing run, this is what I called LIGO A+. This is when LIGO reaches its full design sensitivity, as is advanced Virgo. They have advanced Virgo Plus, and then Kagra reaches the design sensitivity. So that's 2025, basically. Obviously, we hope the field does not end at 2025. So naturally, people have already started to think about where is the field going in the future. So this is now a set of noise curves that show essentially people's aspirations for what the gravitational wave network is going to look like in the 2030s and beyond. So sort of at the very top of the plot, you have advanced LIGO and O3. And then you have sort of in blue, what is the 2025 version of LIGO, which is LIGO A+. That's what we call sort of the second generation of instruments. The first generation was a decade ago. And so naturally people are now talking about, what about a third generation, right? So there are some concepts which I'll talk about now about how to get basically from the second generation to this third generation of more sensitive instruments. I should also mention, and I didn't put it on the plot, that when we're talking about the 2030s, of course, LISA will also be online. I think LISA is scheduled to fly in 2034. So one of these concepts is called LIGO Voyager. So LIGO Voyager is meant to answer the question, what do you do with the LIGO facilities after 2025? So this is not something that LIGO has decided on, but it is a possibility. It's something that LIGO could do after LIGO A+ has collected a sufficient amount of data. And the basic idea here to make a sensitivity improvement is the existing LIGO technology is susceptible to thermal distortion because silica has a coefficient of thermal expansion. So Voyager says, okay, well, let's switch to silicon. Now let's cool it to 123 Kelvin, which is this magic temperature where the thermal expansion of silicon goes to 0. And so you end up with an instrument that is much less susceptible to thermal distortion, so you can pump in more power. So that's how you get a higher power instrument. And that's how you get more sensitivity. So that's sort of, in a nutshell, that's the LIGO Voyager concept. I should say that also, that's not the only improvement. We also intend to have better coatings, more squeezed light, Newtonian noise suppression. But so that is a possibility for what the LIGO facilities intend to do in the 2030s. You might also ask, can we build new facilities? The answer is we can if we have money. That's always an ongoing quest. But so one of these concepts for a new facility is an Australian 4-kilometer facility, which is called NEMO, the Neutron Star Extreme Matter Observatory. Here, the idea is that you would build an instrument that would focus exclusively on sort of the higher frequency end of the gravitational wave spectrum, which means focusing on, among other things, on neutron star signals. So this plot is showing you strain. The blue shows you the energy spectrum of a neutron star collision. And what you see at high frequency is almost a regular structure, and that's the post-merger feature. So that's where the matter effects totally dominate the signal. So that tells you about the interior of the neutron star. And you see in white the NEMO sensitivity curve that, you know, sort of, it shows you that it's a factor of maybe 5 or 6 improvement over advanced LIGO. And so what does that get you? So what the NEMO folks have figured out is that, well, if you only have LIGO A+, you try to observe a post-merger signal, you miss a lot of the information in the tail end of the signal. So the white here is the injected signal, the post-merger signal from the neutron star. The red is how LIGO A+ would reconstruct the signal. You actually track it fairly well. So the goal with NEMO is to really enhance the second generation network by capturing information that would otherwise be lost in the post-merger part of the neutron star in spiral. Einstein Telescope, this is a European concept for an underground 10-kilometer facility. The location's been narrowed down either to Sardinia or Maastricht. It's triangular. The 6 detectors are arranged so that you have 3 low temperature detectors, 3 high temperature detectors. That gets you low frequency and high frequency performance. The nice thing about a triangle is that you sense both polarizations, and you also you could make a null stream for consistency checks. Because it's underground, you would observe down to a few hertz, which is better than you can do up on the surface. The status of Einstein Telescope is they're trying to get on the European funding roadmap for the coming decade, and so it's called S-free. But they produced a science case, a technical design report, a costing study, and the idea is that if the funding comes in, then the construction begins at the end of the 2020s, and it would be observing in the early 2030s. And they already have some preliminary funding to build a Pathfinder facility, so a laboratory to serve as a technology test bed for a lot of the new technologies that would be employed. So there's also a sort of a US focused concept which is Cosmic Explorer. This takes a bit of a different tack. It basically just tries to scale up LIGO by a factor of 10. So it's a surface facility. It would be 40 kilometers long, L-shaped. Instead of having 6 detectors, we would just try to keep it to 1. And the idea is in the 2030s, we can use sort of the existing or extension of the existing sort of A+ style room temperature glass technology. And then in the 2040s, we would switch to potentially switch to a Voyager technology, depending on how the Voyager technology pans out. One of the things that we're working on now, just as a point of interest, is we say 40 kilometers, but we sort of wonder whether we should go, should we also have a 20 kilometer, or do we have to choose between 40 and 20? And the reason is that 40 kilometers actually, because of the light travel time down the arms, ends up being sort of insensitive to gravitational waves at the post-merger frequency, so somewhere between 2 and 4 kilohertz. So we're undertaking a design study right now to try to understand. It's broader than just this question, but this is one of the main questions that we're trying to figure out: is it advantageous to have 40 plus 20, only 40, or only 20? And this obviously has implications for multi-messenger observations, because post-merger signals are a great multi-messenger target. So it's something that we're trying to figure out. In terms of timeline, so we're here in the early 2020s. We're working on an NSF-funded horizon study that contains this sort of trade study and a couple other things. We also would like to start constructing at the end of the 2020s, with the goal of observing in sort of 2035. And then, as I said, this is sort of a multi-stage operation. So the idea is that we would, after sort of in the same way that LIGO and Virgo, all of these initial and advanced stages, we imagine that we would eventually take out the initial detector, the initial CE detector, and put in this better 2040s detector. So that's sort of the trajectory of Cosmic Explorer. So sort of thinking a bit more about the science. So if you look at if you take the strain curves and you translate them into sort of detectability horizons, so how far out into the universe can these various detectors see, you end up with this sort of plot. It has mass, system mass on the horizontal axis, it has redshift on the vertical axis. And sort of the story that emerges here is that, if you look at existing detectors like LIGO, they'll see out to a redshift of maybe 2 or 3 for heavy systems. For the light systems, for neutron stars, it's still very much local universe. It's a Z of 0.1. Upgrades like Voyager will enhance this. So we'll get out for neutron stars to a Z of 0.5 and black holes up to a Z of 8, maybe. But it's really not until you build these larger facilities that you're able to get out to, really high redshift, like beyond 10. So CE and ET will be able to, at full sensitivity, get out to a Z of 100. So sort of territory where you can look for things like primordial black holes. Sort of the other way that you can make a plot basically is to show the various populations of neutron stars and black holes as a function of redshift. And so this plot now shows, on the radial axis, it shows redshift. On the left-hand side, it shows you a population of neutron stars. On the right-hand side, it shows you a population of black holes, 30 solar mass black holes. And then the colored bands show you how far out the various detectors are going to be able to see. So again, it's sort of the same story as I told in the previous slide. If you look at neutron stars in particular, the existing detectors really, they hardly see any. I know that we say that we're going to have a certain detection rate in 2025, and that's great. But in the grand scheme of things, in terms of how many neutron stars there are total, the current detectors don't really see very many at all. And so if we build these new facilities, we'll be able to see basically all of the neutron star and black hole coalescences in the universe that happen every year. So it's really it's a sea change in terms of going from detectors that are in some sense just barely sensitive enough to detect neutron stars and black holes to detectors that are primed to detect basically everything. And so I'll finish with this summary wheel that Satya at Penn State has made for what the next generation network is going to, what science we want to do, right? So there are many science targets. It's a very rich field that hasn't been probed yet. Sort of we organize it into this sort of these themes of precision cosmology, sort of extreme matter, extreme environments, extreme gravity, fundamental physics, and then sort of black holes throughout cosmic time, going back to the edge of the universe. So thank you. Take questions.